Hello everyone, Jai Hind. This is Shailza, Assistant Professor in IT Department at AKGEC Engineering College. So today my presentation is on the topic Modes of Input-Output Data Transfer in Computer Organization Architecture subject. So what is mode of transfer? So we basically use modes of transfer to transfer anything from our keyboard, mouse to CPU. So, but they are not getting directly transferred. We need an interface between them, and that interface is known as input-output interface. So, what is the need of this input-output interface? The CPU merely executes the input-output transaction and may accept the data temporarily, but the ultimate source or destination is the memory unit. So, data transfer between the CPU and input-output devices, which are keyboard, mouse, pen drive, anything else, may be handled in a variety of modes. So there are basically three modes. First is program input output, second one is interrupt initiated input output, and the third one is direct memory access. First I will briefly discuss about these three modes, then I will go in more detail. So program input output operations are the result of input output instructions written in the computer program, and usually the data transfer is to and from a CPU register and peripheral. Now what is peripheral? Peripheral devices are our input output devices, which are keyboard, mouse, monitor, etc. So the instructions are needed to transfer the data to and from CPU and memory in program input output. When the data transferring under program control requires constant monitoring of peripheral by the CPU. Once our data transfer is initiated, then the CPU is required to monitor the interface to see when a transfer can again be made. So in this mode, the constant monitoring of CPU or constant monitoring of input-output devices required. And in program input-output method, the CPU stays in a program loop until the input-output unit indicates that it is ready for data transfer. Why it is in continuous loop? Because sometimes the device is not ready and CPU is checking the status of device again and again. So the CPU will come in a loop until the input-output unit is actually ready for the data transfer. So this is a very time-consuming process, since it keeps a processor busy needlessly, and CPU is the important part of any system, any computer system. It needs to be free, but we are here wasting the CPU time by keeping in monitoring stage to check the input-output device whether it is ready or not. So, but this program input-output can be avoided by using the interrupt facility. Now, what is interrupt? Interrupt is any special command which interface give the CPU that the input-output device is ready for data transfer. The data is available for transfer. So we can use this interrupt facility to transfer the data. And in the meantime, CPU can proceed to execute another program, while the interface meanwhile keeps monitoring the device. It means when any device is ready for data transfer, then the CPU check the state. When the device is ready, then it provide an interrupt to CPU that I am ready and can transfer the data. So CPU give the transferring instruction and it do some another work. It doesn't monitor all the time like program input output. When the interface determines that the device is ready for data transfer, it generates any interrupt request to the computer. And upon detecting the external interrupt signal, the CPU will momentarily stop the task it is processing. Whatever it is doing, it momentarily stop at that time, and it stores the address, or you can say branch to a service program to process the input-output transfer. And after transferring it back, it then returns to the task it was originally performing. And the third mode of transfer is DMA. Now, why we need DMA? We are programmed input output, but it constantly monitoring and wasting the CPU time. Then we have interrupt initiated programmed input, interrupt initiated in data transfer. Now, what is the need of DMA? The interrupt initiated data transfer very few data at a time, but in this these new techniques, new systems transfer whole bunch of data, more data at a time. So interrupt initiated input output transfer can't transfer that very large bytes. To transfer large volume, we need DMA. DMA means direct memory access. So it takes the authority of bus from the CPU, and CPU start doing another work, and the DMA takes the control of whole buses to transfer the data, to transfer the large volume of data. So the transfer of data under programmed input output is between CPU and peripheral without any intervention of CPU processor. So in target direct memory access, the interface transfer data into and out of the memory unit through the memory bus, and it takes DMA controller takes the authority of bus from the CPU. CPU initiates the transfer by supplying the interface with the starting address and the number of words needed to be transferring, and then proceeds to execute another task. And when the transfer is made, the DMA requests memory cycles through the memory bus. So the first task is when the request is granted by the memory controller, the DMA transfer the data directly into memory, and the CPU merely delays its memory access operations to allow the direct memory input output transfer. Since peripheral speed is usually slower than the processor speed, input output memory transfer are infrequent compared to the processor access to memory. So here is an example of programmed input output. In the programmed input output method, the input output device does not have direct access to memory. So a transfer from an input output device to memory requires the execution of several instructions by the CPU, including an input instruction to transfer the data from the device to the CPU, and a store instruction to transfer the data from CPU to memory. And the device transfer bytes of data one at a time as they are available. As soon as they are available, the byte one by one is transferred. And when a byte of data is available, the device places it in the input output bus. This is the input output bus. So whenever the data is available, the device places the data in input output bus, and after that it will set the data valid line. It set DV means data valid line to 1. And the interface, this is the input output interface, it accepts the byte into the data register. It stores the data which was in input output device, it passes the data through input output bus and store in the data register. Or you can say accept the byte into this data register and enables the data accepted line. This is the data accepted line, it enabled it. And after that, the interface sets a bit in the status register. This is the status register. It said that we have data in our data register, and here we set the data register by using flag bit. So we set the flag bit to F. Now the device can now disable the data valid line after transferring the data, but it will not transfer another byte until the data accepted line is disabled by the interface. So the data valid line will be enabled by input output device, and data accepted line will be enabled and disabled by interface. So the device is not able to transfer another byte until the data accepted line is disabled by the interface. So a program is written for the computer to check the flag in the status register. That's why it is known as program input output, because there is a program is written to check the flag in the status. This is a flag and it has to be checked again and again. So a program is written for the computer to check the flag in the status register, which determine if a byte has been placed in the data register by the input output device. And this is done by reading the status register into a CPU register and checking the value of the flag bit. So if flag is equal to 1, means there is data. The CPU reads the data from the data register. Interface has set the flag is equal to 1. It means there is a data and we can read it. If the flag bit is then cleared to 0 after transferring of data by either the CPU or the interface. Interface and CPU both can clear the flag bit depending upon how the interface circuits are designed. It depends upon the design of interface circuits, whether CPU has to clear this flag bit or interface has to clear. Once the flag bit is cleared, the interface disables the data accepted line. So this is the flag bit. It is either cleared by interface or by CPU depending upon the design. If it is cleared, then data accepted line will also need to be disabled. Only that after that input output device is able to send the next byte. So the once the flag is cleared, the interface disables the data accepted line, and then the device can then transfer the next data byte. Only after clearing this and disabling this, input output device can send the next byte. Now it is assumed that the device is sending a sequence of bytes that must be stored in memory, and the transfer of each byte requires 3 instructions. First is read the status register. This is first, read the status register, then check the status of flag bit and branch to step 1 if not set, or to step 3 if set. So status register, initially transferring of data, it has to check the data register, status register, and after sending 1 byte, it has to again check the status register. If the flag bit is, if it is not set, then it has to, if it is not set, or to step 3 if set. If it is set, means if it is 1, then it go to step 3, and if it is not set, means it is 0, then it can again read the data. So the difference in information transfer rate between the CPU and the input output device makes this type of transfer inefficient. Means the CPU transfer the rate in very fast manner, but the input output device doesn't match that speed. So there is a type of transfer inefficient. Next, each byte is read into a CPU register and then transferred to memory with the store instruction. Ultimately, we have to store the data in memory, and that can be done through another instruction, which is store instruction. So each byte is read into CPU register and then transferred to memory with the memory instruction. A common input-output programming task is to transfer a block of words from an input-output device and store them in a memory buffer. The programmed input-output method is particularly useful in small, low-speed computers or in systems that are dedicated to monitor a device continuously. Why dedicated to monitor a device continuously? Because we have to check the status register again and again, whether the input-output device is ready for data transfer or not. So this type of program input-output transfer is only beneficial in small low-speed computers and in the system that are dedicated to monitor a device continuously. The difference in information transfer rate between the CPU and the input-output device makes this type of transfer inefficient. One is very fast, another is very slow. So is the data rate mismatch. So this type of programmed input-output is very inefficient transfer type. To see, here is an example in which we can see how it is inefficient. So consider a typical computer that can execute the two instructions that reads the status register and check the flag in 1 microsecond. Okay, it will check the flag in 1 microsecond. Assume that the input device transferred its data at an average rate of 100 bytes per second, 100 bpps. This is equivalent to 1 byte every 10,000 microsecond. So this means the CPU will check the flag 10,000 times between each transfer. The CPU is wasting time while checking the flag instead of doing some another useful processing task. Our ultimate goal is to make the CPU free or to make it work. We want to make it work but on useful processes. So we can't waste the CPU time just merely checking this flag. So to solve this problem, we have interrupt. And we use this interrupt in interrupt initiated input output data transfer. This is an alternative to the CPU constantly monitoring the flag. Now CPU will not check, CPU will get the information. CPU will get interrupted that the device is ready for data transfer. No need to check or waste CPU's time again and again, just check the flag. So CPU constantly monitoring the flag is to let the interface inform the computer when it is ready to transfer data. So that's why this mode of data transfer uses the interrupt facility and is known as interrupt initiated input output. While the CPU is running, when the CPU was doing any execution, any program, it does not check the flag now in interrupt initiated input output. However, when the flag is set, the computer is momentarily interrupted. When the flag gets set in input output interface, then the CPU will get interrupted for very momentary second from proceeding with the current program. Whatever program CPU is executing, it will get halt for very small time and is informed of the fact that the flag has been set. Now the CPU deviates from what it is doing to take care of the input output transfer. It stops the whatever program it is doing and take care of the input output transfer. After the transfer is completed, the computer returns to the previous program which it was doing to continue. Now the CPU responds to the interrupt signal. This is the main point. The CPU responds to the interrupt signal by storing the return address from the program counter into a memory stack. So it stores the address of program in program counter and then responds to the interrupt signal. And then control branches to a service routine that processes the required input output transfer. Now there are two methods to accomplish this. One is vectored interrupt and the other is non-vectored interrupt. Now in a non-vectored interrupt, the branch address is assigned to a fixed location. The branch address of a program is assigned to a fixed location in the memory. And in vector interrupt, the source that interrupt supplies the branch information to the computer. This information is called the interrupt vector. And in some computers, the interrupt vector is the first address of the input output service routine. And in other computers, the interrupt vector is an address that points to a location in memory where the beginning address of the input output service is routine. So this was all about the interrupt initiated. The main point is input output interface interrupt the CPU when the device is ready for data transfer. Now the disadvantages of interrupt initiated input output is that it can't transfer the huge data. It can transfer very few data byte in terms of bytes. In bytes it can transfer there. Now to transfer huge data, we require DMA, direct memory access. So in DMA transfer, we have a DMA controller. which act as a slave CPU, slave processor. There are two type of processors, master and slave. Master is CPU and another one is, we are using here DMA controller, which acts as a slave processor. Now DMA controller has to share the bus with the processor to make the data transfer. The device that holds the bus at a given time is called bus master. Now here we are CPU, which holds the control of buses. So the CPU here is bus master and DMA shares the buses from the CPU. So here is it acts as a slave bus slave. Now when a transfer from input output device to the memory or vice versa has to be made, input output peripheral device sends a DMA request. So these are the input output or peripheral devices. When there is a requirement of data transfer between input output and memory, it sends the DMA request to direct memory access controller. After sending the request, if the DMA controller is free, it requests the control of the bus from the processor by raising the bus request signal. Now, if DMA is not doing any another work, if it is free, it sends the bus request to CPU that it wants control of buses to transfer the data between these input output devices to the memory. Now the processor stops the execution of the current program and increments the program counter. It means it stores the address of whatever program it is doing, whatever the task it is doing, it stores the address of that program in program counter and moves data over stack and then sends a DMA select signal to DMA controller over the address bus. So when the DMA controller sends the bus request to the CPU, it sets the DMA select request through address bus. Here is the read, write and address data. Here is the address bus and CPU send the request through address bus to DMA controller, that DMA select. Now the DS data DMA select and RS register select lines are activated by addressing the DMA controller. So these two are activated by addressing the DMA controller. And here read and write are control signal which specify whether the data has to read or write. Now CPU, before giving the buses control, CPU provides the following information using read, write and address data lines first. These are read, write and address data lines. So the CPU provide three kind of information before granting the bus to controller. First is address register, second is word count register and third is controller register. Now what is address register? It is used by CPU to specify first address of memory from where to start transfer. So it sets the starting address from where the data transfer is to be started. Next is word count register. It is also used by CPU, means CPU gives the information of word count register and it specifies number of words to be transferred, means how many number of words to be transferred, and it keeps decrementing this word count register by one at a time till it is to 0 and after that it stops. Next is control register. It is used by CPU to specify which operation to perform, means we have to read or write. Input output peripheral device has to read the data from memory or to write the data in memory. So these three information are provided by CPU to DMA and after that it will give the control of buses to DMA. Now processor grants the bus to the controller by raising the bus grant signal now. So after sending the bus request to CPU and providing the details of these three, address register, word count register and control register, CPU will provide the bus grant signal to BG, means bus grant signal to DMA. Now DMA controller is the bus master. And the DMA acknowledge line is set when the system is ready to initiate data transfer. When the input-output peripheral device send the DMA request to DMA controller, after specifying all previous information by CPU to DMA controller, DMA send the DMA acknowledge to input-output device that I am ready now to transfer the data. Now, after assigning the data transfer task to the DMA controller, instead of waiting idly till completion of data transfer, the processor resumes the execution of program after retrieving the instruction from the stack. So, DMA controller now has the full control of buses and can interact directly with memory and input-output devices, independent of CPU. Now, CPU intervention is not required. CPU is not required after granting the bus to DMA controller. DMA controller will use the read, write, and address lines for transferring the data from input-output device to memory. And after completion of data transfer, and how it will get to know whether the data is complete or not, it will use the word count register. If word count registers reach to 0, it means the completion is done. And after completion of data transfer, means when the word count register value is 0, it informs the CPU by generating an interrupt signal. Here it again generates the interrupt signal and tell the computer system, that CPU, that our transfer is complete. Now it disables the bus request. First, DMA will disable the bus request and then CPU disable the bus grant, thereby moving control of buses to the CPU. Now the control of buses is again with the CPU after transferring the data. Now the DMA transfer the data in 3 modes, which include burst mode, cycle stealing mode, and transfer mode. So in burst mode, the DMA hand over the buses to the CPU only after the completion of whole data transfer. Meanwhile, if the CPU requires the bus, it has to stay idle or wait for data transfer. And in cycle stealing mode, DMA gives control of buses to the CPU after transfer of every byte. After every byte, DMA gives the control to CPU and it continuously issues a request for bus control. It again and again issues a bus control request, makes a transfer of 1 byte and returns the bus. By this, CPU does not have to wait for a long time if it needs a bus for higher priority tasks. Otherwise, if this mode is not there, then CPU get hanged. It will not do any work. So it is required for the frequency of CPU, and burst mode is required to transfer the data in huge volume. And the third mode is transfer mode. Here DMA transfer data only when CPU is executing instruction which does not require the use of buses. Okay, that's all about the DMA control. Thank you.